Yeah, hi everyone. Can you hear me? Okay, yeah. We'll wait a couple of minutes and we'll start. No, I will share the for just give me- just let me. I have shared the link. Can you check whether you are able to access it? Yes, sir. No. Can I get some responses? Am I audible? No, you are not able to access. Okay. Did you see the doc which I have shared? Chart is disabled. Mm, mhm. One second. Where I can share it? Uh, just give me a minute. Yeah, yeah. Can you check it now? Can you check it now? I think I have shared in the chart. Is it visible? Can you access it? Okay, okay, great. Yeah, I we can get started then. Um, Let me share my screen. Yeah, are you able to see my screen? Okay. Yeah, we'll try to see the agenda for today's class. Um, um, Today's class, we will talk more about time and space complexity. Um, this is the main agenda. We'll try to cover time and space complexity. Yesterday we see what is an algorithm. We have seen what is an algorithm. Like algorithm is like it is nothing but step by step instructions or unambiguous instructions, to solve a problem. Right? This is what we have seen yesterday. Um, I just want to like, how do you decide or how do you analyze an algorithm, or how do you decide which algorithm is better? Let's say you have two algorithms, algo 1 and algo 2, and you have to tell which algorithm is better. How do you decide that? Anyone, any ideas? Any ideas? Anybody wants to answer? Yes or no? That has best time and space complexity, we are going to select. Okay. Yeah, yeah, that is correct. So we basically decide based on the time and space complexity. Okay. And we'll see what is time and space complexity. We'll talk about that little later. Let's say uh, maybe what I can ask is like, what can be a what can be a good factor to decide which algorithm is the best? What can be a good factor? Let's say one more thing. Let's say we have algorithm 1 and we have algorithm 1 same, like code wise both are same. Code wise both are same. Let's say the first algorithm is using written in Python and the other algorithm is written in C++ or Java, or maybe the first algorithm is written in Mac OS and other algorithm is written in Windows. And maybe what I can say, the new first algorithm is older laptop and the same algorithm is written Windows, it is a newer laptop. Can we consider these factors? Like, can we consider these factors like programming language or operating system, etc.? Can we consider all of this? Chart is disabled. Hi team, if can you help me with disabling the chart, enabling the chart for the students? Just give me a minute. I think I don't have the option to do that. I think I have to check. Yesterday also, some team member enabled it. I think still they are not responding for now. Can you not able to answer in Q&A chat at least? Yes or no? Will that be fine? For now, yeah. For now, use Q&A tab. Maybe I will try to check with them. Okay. Okay, fine. That's great. We can go ahead with the Q&A tab for now. Yeah. Let's come back to the class again. Like, do you think can we consider factors like programming language, operating system, or whether it is a older system, newer system, a lot of external factors for deciding whether an algorithm is better than the other? Yes. Do you think we can consider? Okay. Yeah. Yeah. These things we should not consider. These things we should not consider. Why? Because these are not under our control. These are not under our control. These are all external factors. These are external factors. We want to decide based on the code. We want to decide based on the code. If the code is same, obviously they should have same time and space complexity. So we have to depend on the factors that do not change based on external factors like this. Clear? So for making sense, why we will not consider these things in deciding time and space complexities? Yes or no? Because that is not fair. Like you wrote a code in a better mission, and the you wrote the same code in some other mission, and time and space complexities are will be different for sure if we consider factors like this. So what we came up with, like we came up with something called number of operations, or number of operations, or we can say number of iterations will decide based on this, and this factor is not going to change based on external things like this. Like suppose if you have algorithm 1 and you wrote on same algorithm in different mission, then both will have same number of operations or same number of iterations. So since we are deciding the time and space complexities based on this, they will have same time and space complexity. And now even if you write in Python, or if you write in different language, still time and space complexity will be same. Time and space complexity will be same. Even if you write in Windows, Mac OS, Linux, whatever operating system you take, if the algorithm is same, time and space complexities will be same. Because what's the reason behind this? We are considering the factor that is not going to change based on the external things. Clear so far? Making sense? Yes or no? Okay, great. Now let's talk about time and space complexity. Let's go about them, each of them. Let's say a few more things. Uh, one more thing. Let's say mm, let's consider few scenarios. Let's say we want to sort numbers. Okay. Um, let's say person one did it in some logarithm of n time, some log n time. Let's say base is 2. Yeah, base is 2. We can consider okay. And n is like we have to sort n numbers. Let's say we have given some numbers like 10, 40, 50, some 30, 25, something like this. You have to sort them. Let's say person one solved in log n operations. We'll see what are operations and all. For now, just assume this thing. And other person solved in n time. So if you try to see uh, which algorithm is better, algorithm is better, which algorithm is better, which algorithm is better. Like let's say we have n equal to let's say for n equal to n is nothing but the numbers like size of the numbers. Here n is 5. Okay, we'll let's say we consider n as some 32. Then log n will take how much operations? Log n base 2 will take logarithm of 32, and then base is kind of 2, which will be 5. It will take 5 operations. And what about the other one? For 32, n will take how many operations? It is going to take 32 operations, right? Or maybe what we can do is like we can consider the other algorithm. It is fine. For now, we consider n by 10, and that will have the make more sense. N by 10, which will be 3.2. Okay. Let's say this is some 500 into log n. Okay. Then we'll have 500 into, which will be, sorry, 100 will be fine to make the calculations easy. Let's say 100 and 100. So for making sense, so for clear, yeah. Like at n equal to 32, which algorithm is better? For n equal to 33 or 32, which algorithm is better? Okay, please repeat one more time, sir. Yeah. So consider a scenario. You are given some numbers. Like for example, I gave 5 numbers. It can be of any number, n can be of any number. Let's say I gave you numbers and you have to sort the numbers. And let's say we calculated the number of operations to do that thing. Like maybe for sorting numbers, what you will do, you can compare both of them. Like let's say you compare these two and you will put the smallest first. You can use different techniques. Let's say you got log 100 into log n operations for solving that problem, and there is another person who did the same thing. I just gave short numbers for the example. You can take any problem. Let's say person one solved that problem using 100 log n operations, and person two solve that problem using n by 10 operations. You have to decide which algorithm is better. And for example, we take n equal to 32, and we calculated the number of operations. For n equal to 32, 100 log n will be 100 into log 32 base 2. Log 32 base 2 will be 5, because 32 will be 2 power 5, and 100 into 5, it will be 500 operations. And for n by 2 algorithm, it takes 3.2 operations. And if you try to see which is smaller, 3.2 operations is smaller. So obviously it is taking the less number of operations. So it is going to take less number of CPU cycles, and it is ultimately going to take less number of time for to run this, execute this algorithm. So at n equal to 32, n by 10 is going to be better algorithm compared to 100 long n. 100 is a constant, just that is the number of operations. That is a function which you represented the number of operations. Yeah, output is both the same. The logic is same. Basically, let's say Maybe let's say what I can let me give one example, maybe that will help you better. Let's say I wanted to calculate uh, um, number of operations. Let's say I want to check, there is a program, I want to check whether n is prime, even or not, even or not. Okay, maybe the program will look like something like this. uh, uh, Boolean and function f, or is even, let's say function name, and it is going to take the number n, and we have to check. How to check? If remainder when divided by 2 is equal to 0, then we can say this is even number, so we will return true. Otherwise what we are going to do, we are going to return false. Like we have this program. Okay, we have to calculate the number of operations or number of iterations for this program. How to do that? Number of operations, how to calculate? Here what we are going to do first, maybe for checking this n modulo 2, for calculating n modulo 2 we need one operation. We'll discuss why this is going to take some constant time operation, and then we have to check equality. For equality check you will take some again constant time. Let's say this time is k1 and this time is k2, and um, and we have to return true. For returning uh, boolean value, again it is going to take constant time. It will be, so total time will be k1 plus k2 plus k3, which will be a constant again. So this is the constant time. Let's say we'll take other example, like let's say I want to have some array A of some n numbers. I have to print this all the numbers. What I will do, I will go and I equal to 0, I less than n, I plus plus. I have to print, let's say print each number. This is the logic. For this thing, what happens, for printing each number, it will take constant time. Let's say which will be some c1. Now for we have to do this times n times, because this loop runs n times, right? So what will be the total time or total number of operations? Total number of operations to execute this program, it will be c1 into n. So here c1 is some constant. Similarly, we are assuming for person 1 it took 100 log n time. So where 100 is one constant and log n. Here in this case, let's say we have, this is one operation. K2 is also some, let's say one operation. This is also take 1 second or 1 millisecond. Total it will take 1 plus 1 plus 1 3 seconds. Here if we consider this as 1, it will be n. So that is what 100 here. So for making sense now, we are just assuming we somehow calculated the number of operations for an algorithm. Let's say wrote by the person 1. Let's say we got 100 log n base 2 operations, and for person 2 we got n by 10 operations. We have to decide which algorithm is better, 100 log n base 2 or n by 10. Making sense? Is the ask is making sense? What I'm asking, or still anybody is having any doubts? Can I get some S's? Yes or no? Okay, great. Now let's say we consider for n equal to 32. We'll talk about the bigger numbers. Let's say we talk about some n equal to 64. I am taking two powers so that calculations will be easy. Then 100 log n will be 100 log n base 2 will be kind of, it will be how much? It will be simply 600 operations, 2 power 6, right? Now for n equal to 64, we'll have n by 10 as we what is the time this will be? It will be 6.4, 6.4 operations. Still n by 10 is better. Let's say we want to take some um, we want to take some which number I can say, some 2 power some 2 power 20, some 2 power 20 we can consider. When n equal to 2 power 20, 100 into log n base 2 will be how much? It will be 2000 operations, 2000 operations. What about n by 10? It will be some 2 power 20 um, divided by 10, which would be somewhere around let's say 2 power 16 into 2 power 16 into 2 power 4 we can write, right? 2 power 16 into 2 power 4, and 2 power 4 which is 16 by 10, 1.6. This is the operations. So 2 power 16 is way better than the 2000 operations. So what I want to try to say here is like, when we consider these two, 100 logarithm n and n by 10, for smaller values n by 10 is better. For larger values 100 log n base 2 is better. So we have to decide what factor we have to consider to decide we have to consider for deciding which algorithm is better. Like we have to do we consider larger values or smaller values? So we have to consider this factor also. So what we have decided, one factor we have decided is number of operations. Second thing is like larger values or smaller values. We have to consider that also, because if we choose smaller values in this case, we have to tell answer as a n by 10. If we consider larger values, we have to tell 100 log n is better. Making sense now? Why we need this factor also? Making sense? Yes or no? Great. Yeah. So we like we usually consider values to be large. So at larger values, whichever algorithm is better, that is the better algorithm. Okay. Why we consider large values? The reason behind is most of the real life or real world applications works on large data. Let's say consider the example of YouTube views we have in billions, or consider the Instagram users we have in some billions or trillions. So we usually deal with large amount of data. That's why we consider always input size as large, and whichever algorithm is better at large values, that we consider as the better algorithm. Making sense? Yes or no? Why do we consider the larger values? So in this case, what we have to choose? We have to choose 100 log n as better algorithm compared to compared to n by 10. Why? Because at large values, 100 log n is giving less number of operations. Is giving less number of operations compared to n by 10. Making sense now? So two things we have decided. For an algorithm to be better, it should have less number of operations. Second thing, whichever is having less number of operations at larger values, that will be the better algorithm. Making sense, right? Why we decided based on the number of factors, and why we need to consider large values. Even that reasoning also making sense. Yeah, great. Yeah, let's go further. So using these observations, basically uh, we have something called asymptotic analysis. So basically what this asymptotic analysis is like, it is used to judge the performance of an algorithm for larger values. Got it? Let's consider three things. Let's consider three things. uh, we have algorithm which takes n operations, and we have an algorithm which takes n into root n, let's say root of n, and we have an algorithm which take n square. Okay, we have to decide which algorithm is better, which um, which of these algorithm is better, which of this algorithm is better. Anyone wants to try? We have for an algorithm, we have three different algorithms for a particular problem. One algorithm is taking odd, n operations. Another algorithm is taking n into square root of n operations, and another algorithm is taking uh, n square operations. And which of these three algorithms are better? And why? N square n into square root of n. Yeah. How you were going to decide? Again, the same thing. We are going to take the larger values. Let's say initially for n equal to 10 or something, what happens for n, it takes 10 operations. For n into 10, it is going to take 10 into root 10. Let's approximately 3 point something. Let's say 30 operations. N square, how much operations it is going to take? It is going to take 100 operations. Let's say 1000. We want to check for the bigger values. 1000. For n algorithm, it is going to take 1000 operations. For n into square root of n, how much it is going to take? 10 into square root of uh, uh, um, 1000 into square root of 1000, which will be 10 root 10, around 30 point something, and into 1000, which will be around some 30,000. Let's say 30,000 or something. Let's say 30k or something. And this will be how much? 10 power 6 something. It will be kind of 1000 into 1000, right? Which will be 1000k. So even when you go to see at larger values or larger inputs, which algorithm is better? Which algorithm is taking less number of operations? N is taking less number of operations. Less number of operations. So the better algorithm or best algorithm in this case is like N. Is it making sense? So basically we have to decide for large values, whichever algorithm is taking less number of operations, that is the best algorithm. So in this case, which is better? Order of this algorithm which is taking n operations will be better. Then which algorithm is better? N into square root of n is better. And then n square will be the thing. So out of these three, n is better then compared to n square and n square root n. N square n into square root of n is better. Clear? Making sense? Are you able to get how you are going to decide which algorithm is better? Great, great. Yeah, let's go forward. So basically, this asymptotic analysis is all about the same thing. We have to decide the judge the performance of an algorithm for larger values. Okay, that is what we are going to do. And we have some notations like um, for example, if you take mostly we will use the big O notation. Like basically what it says, it follows some rules. um, we have to calculate number of operations with respect to input. With respect to input. And then what we have to do, we have to neglect uh, lower order terms. I will explain what this means. And then what we have to do, the next thing what we have to do is like we have to neglect coefficients, or we can simply say the constant terms, constant coefficients we have to neglect. So basically what it is saying is like, let's say these are the number of operations, right? Let's say for me, if I calculated the number of operations for an algorithm, let's say I got something like 3 into n square plus some uh, 2 into n, and there's some 5. So this is the number of operations, like number of operations in terms of input, number of operations in terms of input, in terms of input. Uh, let's say for example how we can calculate is like, let's say uh, we have some function, random function, uh, which takes some input n, and then what happened is like we have some loop, we have some loop. One loop is like it only runs 2 times. Yeah, I have one more doubt. Why so many Gopal Singh has joined? Okay, you can answer it. Maybe I will continue with the class. Yeah. Let's say I have something like this, and I have something like j, some random operation. I have to print something, some print message, I or something, and I have to decide something like this. And maybe let's say I have some int array or something. I'm writing some random algorithm just to make sure you are understanding why we can get something like this kind of operations. In some k equal to 0, k less than n, k plus plus, we have to print hello. Okay, and yeah, something like this. If you try to see what happened for this algorithm, we wanted to run this loop k times, and for each operations what is it is happening, we are checking. One is we are checking k less than 1, n or not. The second thing, we are incrementing 1. So this will take one operation, this is taking one operation, printing is going to take one operation, and we are going to take 3 operations. And how many times this iteration is going to take? It is going to take n times. So for this it is going to take 3 into n operations. And also if you try to see how many times this high is printing, it is printing n times for each iteration we have. So this is running n times, and this outer loop runs 3 times. Outer loop runs 3 times, and this loop runs, inner loop runs n times. And in each time what it is doing, it is doing printing, it is going to do uh, check this j less than or n, or it is also going to do the increment, let's say 3 operations. So it is going to do 3 into n times and again the outer loop is running 3 times, and in each thing we are having 2 more times. So 6n into 3, almost it is going to be 18n square kind of thing. So we are going to get something like some 18 into n into square. So when we want to calculate all of these things, we are going to add total time taken. So 18n square plus 3 into n, something like this. So there is a chance we can get some kind of uh, polynomial expression in terms of input. Here, let's say I got something like this. When I got something like this, what this asymptotic analysis or big O notation says is like, ignore the lower order terms. Here, what is the higher order term? Second degree, or this n square is the higher order term. We can ignore all of these things. So what we can do, we can um, we can remove them. We need not consider them. So again, what else we can do? We have to neglect constant coefficient. Here we can neglect the coefficient for the higher order. So what will be your final time notation, which will be n square. Your you have the number of operations will be n square. So this is what we are going to say as the time complexity. So time complexity in terms of big O, which will be order of n square. So we are basically, what we are trying to say is like, we basically, when we try to calculate like this way, it is going to take extra work. What we are trying to do, we are trying to reduce ourselves some kind, simplify some work, so that we can easily calculate what time a particular algorithm take. That is what this asymptotic analysis will do. So if I want to summarize what we have discussed so far, we want to judge performance in algorithm, like which algorithm is better. We understand first thing, we should not depend on things that change. We should not depend on things that change, like software, hardware, operating system, programming language, etc. We will only consider, we consider number of operations with respect to input size. And second thing, what we are going to do, we are going to uh, uh, we are going to choose, we are going to consider for larger values, not for the smaller values, because we deal with larger data in real world. Now what, this is what we are going to do. And upon, for further simplification, what we will do, we will ignore lower order terms. Second thing, we will ignore constant coefficients. So this is what we are going to do to calculate time or space complexity. How it is going to run? Yeah, sorry, it is going to run 2 times only. Clear? Yes or no? Yeah, sorry, I think I corrected it. Yeah, it will run only 2 times. So for making sense, what is, why do how this time and space complexity will help you? Yeah, if you understand the intuition behind time and space complexities, let's go and see each of them. Let's go ahead with the space complexity. Like basically space complexity is nothing but total space taken by the algorithm with respect to input size at any given point of or during the execution of the program, during the execution of program, or not, we can say maximum space. Let's say what happened, uh, uh, what I can say is like, let's say uh, we need one example. Let's say uh, we wanted to take input n equal to input. Basically we take input from the user. Like say we take input from the user. Let's say n is integer. We take integer input from the user. Let's say integer input from the user. Then next we wanted to have something like uh, we want to check whether it is even or not. Let's say I will check if uh, n when divided by 2, if the remainder is 0, I'm going to return true, otherwise I'm going to return false, right? Here if I try to check what I need, I need for this program to execute, I need one variable, that is n, and n is an integer. How much space I required for it? I required some 8 bytes. Like it depends on the compiler. For now we assume that 8 bytes. For integer it takes 8 bytes. So I need this amount of space. And what I try to explain from the space complexity, we have to represent in terms of input size. So for in terms of input size, how can I represent? I can put n power 0, and then I have uh, n power, sorry, n power 1, so on. This is what I want to represent in terms of n. If I want to represent 8, what I can do, I can write 8 into n power 0. I can write 8 into n power 0, right? And if you try to follow this thing, we can ignore lower order terms, and there are no lower order terms, and we can ignore constant coefficient. So here what we can ignore 8. So for this the complexity is n power 0, which is nothing but constant. So the space for this is like constant. Space complexity is constant for this algorithm. Is it making sense? So basically, what is the space complexity? It is the maximum space taken by the algorithm during the execution of a program with respect to input size. Here it took uh, 8 into n power 0, and we can ignore 8 constant, and n power 0 is constant. That is what the space complexity. Let's take example 2. Let's say you have some integer array and you store some kind of n numbers. How many, what is the space that you required, like maximum amount of space required during the execution of the program? We have how many integers? We need n integers, right? we have to store n integers. For each integer, how much space we are going to take? We are going to take how much? 1 byte, or sorry, 8 bytes. Now for n integers, how much space you are going to require? We require 8 into n bytes. Now so what is the space complexity? We have expressed in terms of input, right? Already 8 into n. There are no lower order terms, or which is nothing but a constant. And we have to ignore our coefficient, constant coefficient, so it is nothing but n power 1. So space complexity will be order of n. Here it is a constant, or we can write big O of n power 0, which is nothing but order of 1. All are same. Clear so far? This thing also making sense? No, time and space complexity will be different for different algorithms. I am giving some example. Here we have this uh, 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 this uh, this is the algorithm we have, and we are not calculating any time complexity now. We are just calculating the space complexity. What is space complexity? It is nothing but the maximum space taken by the algorithm during the execution of the program, and we have to calculate with respect to input size. For this algorithm, if you try to see, we want only one variable, which is nothing but integer. For storing that, we require 8 bytes, and so we want to express 8 in terms of input. So we can't represent any of the other powers, so we represent it using 8 into n power 0. Since as per this asymptotic analysis or big O notation, we have to remove the constant coefficient, so we left with order of n into n power 0, which is nothing but the order of 1. In other words, we call that as the constant. And for this algorithm, we have to store int array of n integers. For storing this, how much space we require? We need n integer space. For each integer, how much space we required? 8 bytes. For n integers, we need 8 into n bytes. So we expressed already in terms of n, which is nothing but the n power 1. And we can ignore constant coefficient, so it will be order big O of n power 1. Making sense how we are going to calculate? No, for now, don't worry about base address and all. We are going to cover that in arrays class. Just try to focus on how to calculate space complexity. Are you able to understand how to calculate? Okay. Let's go ahead. Yeah. Let's say, can you calculate for this algorithm how much space we require? What is the space complexity for this algorithm? You have to store n square integers. This is like a matrix, right? Matrix representation. Let's say you have some a of 2 3 uh, 2 3. Like maybe how your matrix will look like. You will have 2 rows and 3 columns. 4 5 6. Here you require 6 elements. Like what about for generic n by n matrix? How much space you required? What is the space complexity? Uh, Someone said 8 into n into n. I am asking about the space complexity. See, uh, okay, in terms of big O notation, what it would be? Yeah, I understand. Here again, we have n into n integers. We know for each integers we take 8 bytes. So for n into n integers, we need 8 into n into n byte space. But when you want to express space complexity, the most important thing, you have to ignore constant coefficients. So it will be order of n square. Remember, this is not equal to order of 8 into n square. This is not correct. Whenever you are representing in terms of big O notation, you should always ignore the constant coefficients. You should, it should, this is the correct one. Order of n square is the correct one. Big O of n square. Clear? Yes or no? Great. Let's answer one more thing. Let's say you have to calculate space complexity for this one. You have to represent n by n matrix. What will be the space complexity? Correct. Yes. It will be again, it is obviously going to take 8 into n into m bytes. But when we want to represent space complexity, we represent using some big O notation. And in that notation, what you have to ignore? We have to ignore the constant coefficient. So it should be order of n into m. Yes or no? Making sense? Okay, clear. Great. So that is about this space complexity. Let's talk about time complexity. Time complexity is nothing but total time taken by the algorithm with respect to input size during the execution of the program. So let's say, and also this is the time complexity. Is the definition making sense? It's basically during the execution of the program, what is the total time taken? That is what time complexity is. And there are few things you can use regularly. Some things like for all arithmetic operations, like plus like addition, subtraction, multiplication, or division. For all of them, you can consider and you can consider constant time or order of one time. And what else, we can have something like input operators, like taking inputs from the user, like in C++ it is like something like cin operator, or in Java you have java.util.scanner. All these things you can consider as constant operation. And output operations like printing, cout, or system.out.println in Java, uh, like basically printing output to the user. You can consider this also operation as a constant time. And we can consider comparison operator, like suppose if you want to check a is greater than or conditions, or a is less than b, or a equal to b, something, any comparison operator, you can simply take constant operation. And other than that, we can consider something like binary operations also takes constant time, like binary operations in that time, like if you want to do a or b, or you can say a and b, like a and a is or b, all operations you can consider as order constant time. And second thing, initialization of the variables, this is also a constant time, like let's say a equal to 5. For this, what is the time taken for it, you can consider it is a constant time. So these are the assumptions you can take always for all arithmetic operations: input operators, output operators, comparison operators, binary operations, initialization of the variables. All these things you can take constant time. Making sense so far? Is the rules also making sense? Yes or no? Okay, great. Let's uh, take some examples. Let's say I want to calculate this example on. Let's take, what is that? What is the time complexity? We have seen calculating the space complexity, right? We need only one variable, that is also n power 0. What is the time complexity for this algorithm? What is the time complexity for this algorithm? Constant. Yes. For this time complexity, we are taking input from the user. What we are doing, it is a constant time complexity. Maybe let's say some k1 or c1. For this also, what is the for this is a check, right? For doing this operation order of one constant, this is also constant. So again, this is a constant time, constant c2. Either this or this will happen, so total time complexity some c1 plus c2. And when we want to express, what we have to do, we have to express in terms of input size. So when we consider n is the input size, since it is a constant, we have to express in terms of n power 0 only. So it will be how, what will be, it will be c plus 1 c plus c1 plus c2 into n power 0. And what our what our this complexity rule says, we have to ignore the constant coefficient, so it will be n power 0. So time complexity will be order of n power 0. which is nothing but order of 1. That will be constant time. Clear? Constant. Why it is constant? It is not n, it is constant time. Making sense? Yes or no? Okay, great. Let me give other example. We have some algorithm int I equal to 0, I less than n, I plus plus. For int j equal to 0, j less than n, j plus plus. Some print high. What is the time complexity for this? Sorry. Did you get the problem? You have to calculate the time complexity for this. What will be the time complexity for this? Some says order of 1, some says order of n square. Okay, let's see. What we have to do? We have to calculate how many times this is printing. For printing, what we have seen, for any printing output to the user, you can assume some constant. Let's say this is C1. And what? How many times this loop is running? This is running almost n plus 1 times, or you can say n times. Okay, it is going to run n times. Okay, I think I have told why n times. Okay, this is going to print n times, but this loop is going to run n plus 1 times. Now in each operations we can have two more constants, j less than n. We are checking, we are going to increment j plus plus also. Let's say we can simply write this thing n times. Okay, and this is also, this outer loop is going to run how many times? It is going to run n times. So this particular statement is going to execute how many times? C1 in into n, and for each of them again it is going to run n times. So it will be C1 into n square. And when we represent in terms of big O notation or something, what we have to do? We have to ignore the constants. So it will be simply order of n square. Are you getting why it is not a constant? Why it is order of n square? Still any doubts why it is order of n? It is clear, right? Okay. Okay, great. Yeah. Now let's say what will be the space complexity for this? Space complexity for this. I'm asking the space complexity for the same algorithm. When it comes to space, you have to see which where I have to store memory. Here, if you try to see, I have two variables I and j. For storing them, I need two integers. Two integers in the sense I need 2 into 8 bytes, which will be 16 bytes. 16 bytes I have to represent in terms of input size, which is n.
So 16 into n power 0. Again, I can ignore the constant coefficient, which will be n power 0. So it will be order of 1 or constant. Making sense? The difference between time and space complexity. Are you able to get it? Okay. See, when calculating time complexity, you have to calculate what is the time taken for running this program. When calculating the space complexity, you have to calculate how much space you required. Here in this program, what you are going to store? You are going to store two things. One is I variable, second thing is j variable. Initially I will be 0, then j will be 1, j will be 0, and you are going to print high. Okay, this is how it is going to work. Then what happens? The next time your j will become 1, again you are going to print high. Then your j will become 2, you are going to print high. Then j becomes 3, high, and so on. Then what happens? Your I becomes 1, again j will start from 0 and you are going to print high. So if you try to see throughout the execution of the program, you just need only two variables, I and j. For storing I, you require 8 bytes. For storing j, you require 8 bytes. You basically need 8 bytes, 16 bytes. And when you want to express in terms of the input size, it will be 16 into n power 0, n power 0. So which will be again a constant. You have to ignore the uh, constant coefficient. Making sense now? Space complexity. Are you able to get the difference between time and space complexity? And also, did you get that time and space complexity need not be same? Yes or no? Okay, great. Let's talk about few more things. Now, let's say for int I equal to 0, I less than n, I into 2, you have to print high. What is the time and space complexity for this? Time and space complexity. Just check it's not order of n. Any idea? Space complexity wise, fine, but time complexity is still wrong. Do you want to try one more time? Correct, correct. Yes. Yeah. Now you're on the right track. Let's say space complexity is quite easy. Throughout the program, what we only have only one variable we have to store, that is I, one integer which will be constant. What about the time complexity? For time complexity, what we are going to do? Initially, I will be 0, and you are going to check some whether I is less than n or not. Let's say that is true, then you are going to print high. Now what your high will become? Uh, then your I is going to become I into 2. Again, it will be 0. So it's keep on running it is infinite loop. I think we can put I as 1. Okay. Now in that case, what happened? For I equal to 1, it is going to print it is. Now I becomes 2. Now what happened? So with I equal to 0, it will be time complexity will be infinite, because you keep on going inside, because I will be 0 always, you will always enter inside and you are going to print it. Now suppose if I change I equal to 1 2, then your time complexity differs. Initially I will be 1, then your I will become 2, you are going to print high, then 2 into 2, it is going to 4, again you are going to print, then 4 into 2, again it is going to 16 and all. Till when you have to do this thing, you have to check 2 power some k, some 2 power k less than n. You can try until this thing. That means k should be less than log n base 2. Till this thing, your thing will work. So what you are going to do, these many times you are executing this print statement. So this printing statement is always going to take constant time, but this is going to execute log n to base 2 times. So it will be order of log n to the base 2, or you can say log n. Making sense? It is not n by 2, it is not order of n, it is log n, because this is not going to execute n times. This loop is going to run log n times only. Clear, not clear? Let's say I have my algorithm is like this. I into I less than n, and I have I plus plus. What will be the time and space complexities? I gave the other algorithms. What is the time and space complexity? Anybody wants to try? Okay, space is constant, that is clear. Space wise it is clear. What about the time? Order of n square root of n. Yeah, it's root of n. Order of log n. Yeah, just think log n is not correct. Yeah, let's say what happens. Space wise, everyone is clear because we have one variable. We are going to use that. Let's say I want to calculate uh, for this thing time. Initially, I will be 1, so I am going to print high. Now for next time, what happen? I am going to check I should be less than n. I into I should be less than n. Next time I becomes 2, I have to check 2 into 2, which will be less than n. Again I am going to print. Again I am going to check 3 into 3. So till when I am going to do this? I am going to do some k into k till I equal to k. I am going to do this, where k should be k into k should be less than n, where k should be less than square root of n. So what happens? This print statement is going to print root of or square root of n times. So your time complexity will be, for printing the statement, it is going to take constant time. This upgrading, all these are constant times. It is going to take constant into square root of n. So time complexity will be square root of n. Clear? Great. Yeah. Just make sure whenever you are in doubt, just try to see how you have to calculate it. You just do not try to guess the answer. Okay. Let's talk about some recursive uh, algorithm. Uh, let's see about uh, some factorial calculation. Like what will be the factorial algorithm? It will be like factorial of n will be like uh, if n equal to 0, return 1. Otherwise, return factorial of factorial of n minus 1 into n. Okay. Like what will be the time and space complexity for this? Time and space complexity for this. Any try? Any idea how you are going to calculate? Just try to calculate based on whatever we have discussed so far. Uh, time order of n, space constant. What it is? Like I like try to distinguish time and space. time constant. Okay. What about the space? Space constant. Okay. Okay. I think let me understand. Like for answering this, you should know how recursion works internally. Works internally. Like what happens in case of recursion? We have recursion stack. Let's say we are at here. We want to calculate factorial of n. Let's say I want to calculate factorial of 5. Factorial of 5. So I go to execute this function. Initially, I will see n is 0, not n 0. So what I want to calculate factorial of 4 into 5. So what I will do, I will go to, I will store this in the stack, factorial of 5. Then what I will do, I will store some line numbers like where I want to reach after completing factorial of n minus 1. So let's say I will keep some 0, 1, 2, 3, something like this. Okay. Now I will, once I got the answer factorial of 4 minus n minus 1, I am going to multiply with this n. So I will have to come back to here. So what I will do, I will have this in my stack. Okay. Now what I will do, I go to factor, I have to calculate factorial of 4. So what I want, again n is not 0, so I have to calculate factorial of 3. So what I will do, I have to go to factorial of 4 here, and I will store that line here, and I will go to factorial of 3. Again I cannot calculate, I have to come back to this thing. I have to go to factor of 2. Again I have to come back to this line, and I have to go to factorial of 1, and then I have to come back, and I have to go to factorial of 0. Okay. Now when I got the factorial of 0, I am going to replace that value here, which is 1, and I have to multiply with what? I have to multiply with that with 1, which will be again 1. Now again for factorial of 2, I have to multiply value of this thing, which will be factorial of 1, and I have to multiply that with the 2. So I will get the 2 here. Again, whenever I completed it, I am going to remove it from the stack. So what I can say is like, I can copy like this way. Uh, so at one point we will have the stack like this. Let's say simply we have like this stack. Now once we reach the base case, what it is going to do, it is going to return to the calling function. So once we are going to slowly, one by one, they are going to remove it. 1 into 0, then 1, 1 into 1, then 1 into 2, then after removing it, 1 into 2 into 3, after removing this, 1 into 2 into 3 into 4, after removing this, 1 into 3 into 4 into 5. That is how factorial is calculated. Is it making sense how internally recursion will work? Yes or no? First of all, is it clear or not clear? Clear, right? So if you try to see, this is the stack space. If we have n function calls, we might need n rows in your stack. So basically you need order of n space. And this is at a given point of time. This is, I am not saying this space is going to be always during the execution of the program. And if you try to see the definition of the space complexities, it is not at any given point of time. It is maximum space. Here at one point you have to take all of these function calls. That's why the space complexity will be order of n. Making sense? Whenever you talk about the space complexities, you always have to consider maximum space that is occupied during the execution of a program. So what will be the space complexity? It will be order of n. What about the time complexity? What about the time complexities? Time complexity is simply, you can say, the number of function calls. In case of recursion, you can simply say the number of function calls into time taken for each function call. What are the number of function calls? If you can see, the number of function calls is n. So it will be order of n. And for each time function call, what you have to do? You have to simply multiply with the n. You know this answer, you know this answer. You just need to multiply. So for multiplication, what time it is going to take? It is going to take constant time, or in other words, it is going to take order of one time, which will be order of n. Is the time complexity also making sense? uh, Anybody wants me to repeat it, or is it clear? And how to calculate for the recursion also, is it making sense? Okay, great, great. Let's see one more thing and we will conclude it. Let's say I want to um, let's say I have some function. What I can say, let's say I have something like f of n, and I have to calculate something like if n equal to 0 or n equal to 1, return n, otherwise return f of n minus 2 plus f of n minus 1. What will be the time and space complexity? Can you try calculating time and space complexity for this? Any idea? Can be 3, sir. Didn't get. Okay, let me explain it. Okay, taking to understand. Okay, yeah. Again, what happens? Try to understand. Let's say I want to calculate f of 5. Now, what I have to do? My Just try to understand how it works internally. 5 is not equal to 0 or 5 is not equal to 1. So I have to call f of 4 and f of 3. So for before calling that, what I have to do? Uh, before so what I have to do before going there, for f of 5, I can't calculate directly. So I have to store it in the stack. Now what I will call? I will call maybe f of 3. This is the first. So I will call f of 3. Again, for f of 3, I have to, for calculating f of 3, what I have to do? I have to go to f of 1. Okay. Now I have reached f of 1. Now my I have n is equal to 1. So I have to return 1. So for this I got 1. And what I have to do? I have to store 1 here. And along with that, what I have to do? I have to calculate f of 4. So f of 4. So now again for 4, what I have to do? Um, I have to go to check these things. It is not working. Again, I have to do f of 2. Then what I have to do? I have to come back to there is no f of 2. Now again f of 0. So what happened? Again f of 0. Now I got my value directly. I have to calculate that. For now, for f of 0, now once I got that, for f of 2, I know 0, I got the value of 1 also. It will be 1. So I know the value of these two, which will be 0 plus 1, 1. Since I know f of 2, now I will go to f of 3. So this way, what we are going to see in the recursion stack, you cannot have more than n function calls at any time, right? Are you able to get it? Like in recursion stack, you cannot have more than n function, right? Yes or no? At most, you will have n functions only throughout the execution of the program, because the other functions are going to uh, uh, removed from the stack. Making sense? Not making sense? I need some yeses or not yeses. Okay. So the space complexity is maximum space that is occupied during the execution of a program in terms of input size. So it will be order of n. Clear? Okay, great. Now what about the time complexity? We should know the number of function calls, total number of function calls. How many function calls? Each function is making two calls, right? Let's say you have one, then from these function you got two function calls. From this, each of them gives two. So it will be 2 powers 2. From each of the 4, you will get two calls. It will be 2 power 2 into 2 power 3. It will be 2 power 3. So and so on. You are going to have n function calls. So 2 power n minus, you simply try to add 1 plus 2 square and so on n times. So you will get some 2 power n function calls. And what is the time for each function call? You just need to add two function call. When you know the answer, you just need to add them. For add, it will take constant time, so it will be order of 2 power 2 power n into constant, which will be order of 2 power n. Making sense? Clear, not clear? Great, great. Yeah. So that is what I want to cover for today's class. So if I want to summarize, for recursive functions, space complexity remains same. Like the definitions are same. What are the time and space complexity definitions? Space complexity means maximum space, and time complexity means total time. In case of recursive, what happens? It becomes, in recursive, it becomes same thing. You can say maximum number of active calls during the execution of a program. Active calls in the sense which are there in the recursion stack. This is what happens in case of recursive. This becomes time complexity is equal to total number of function calls into time for each function call, time taken for each function call. This is the, yeah, this is the main thing. This is what we have seen about recursion, and in asymptotic analysis, what we have seen, uh, the main thing is like we have to ignore the lower order terms. Second thing, we have to ignore the constant coefficients. And also when calculating the algorithm, we always do not consider the external factors. We only consider the factors that do not change, like number of operations. And we also consider for larger values only, because we always deal with large data in real world. These are the main points that we discussed in this class. I want to take doubts. Maybe I will wait for a couple of minutes. We're also almost, uh, the time is up. Maybe if anybody wants to ask some questions, you can ask. Otherwise, we can drop. Any doubts, anybody? I will share these notes tomorrow. How's last conclusive part? Uh, like last conclusive part in the sense time complexity calculation, or this in recursive time complexity, how we come up with. Can you elaborate that part? Okay, okay. I'm showing the last part on. Okay. Recursive time complexity only. It is nothing but total number of function calls into time taken for each function call. That is also same as like total time taken for the execution of the program. Are you able to see it? Okay, okay, great. Any doubts? Okay, okay, yeah. Thank you. Thanks everyone for joining. I think we'll meet in next class. Yeah, yeah. Thank you, everyone. Yeah, good night. I will stop sharing. Yeah, yeah. I will end the class. Yeah. Good night. Yeah. Thank you.